Hi, this is Dane Quinn from the University of Akron, and today I would like to discuss modal analysis, and this is for fundamentals of mechanical vibrations. So here's the general idea. We have our multi-degree of freedom system here, mx double dot plus kx equals F, where F is some generic forcing term, and I would like to solve this. So to produce the response, x of t, which is, again, some unknown function that we would determine in the solution procedure. Well, this starts off with n coupled equations. And that can be difficult to solve. Right? Again, we have n equations here. All the different variables could appear in all the equations. Right? So again, this is a fairly complex system. Well, we have a procedure referred to as modal analysis that can help simplify this and essentially take these n coupled equations and turn them into n uncoupled equations. Right, so each equation would only have one coordinate. And this is based on using this idea of orthogonality of the mode shapes. Right, so we saw this previously, that ui, where u is a mode vector, times the mass matrix, times a different mode vector equals 0. And likewise, ui transpose times the stiffness matrix also equals 0. And of course, this is for lambda I, lambda not equal to lambda j. Right, so if the eigenvalues are distinct, then we have these nice properties. And this allows us to ultimately write a set of equations that look like q double dot plus lambda times q equals some forcing function. And all of this remains to be determined in this lecture. Right? But essentially these are modal coordinates. Lambda here is the eigenvalue. And notice that this equation essentially amounts to a single degree of freedom undamped forced equation. Again, we have no damping here in the original system. Well, this actually is fairly easy to solve. Right? So I can go and solve each one of these for these different modal coordinates. And once I have the modal coordinates, I can reconstruct the original solution. Right, so x of t here was equal to the sum over all of the different modal coordinates, qj times the mode shape. Right, and we've already seen this previously when we talked about properties of the eigenvectors, or u, the mode shapes. Right, so again, this modal analysis procedure simplifies the solution of these general n degree of freedom, multi-degree of freedom systems. Right, so basically, rather than taking this direct path, we decouple the equations, we solve those decoupled equations, and then we reconstruct the solution. Right, and the n single degree of freedom systems that are represented in terms of the modal coordinates are often easier to solve. Right, because again, the equations are essentially reduced down to a single degree of freedom system. Right, so these are easier to solve, but we have to do it n times versus this one equation which has n coupled equations within it. So this is the general idea behind modal analysis. Right, so let's go and figure out how this procedure works. Right, so we'll remember a couple of things. These mode shapes, the u's, which are eigenvalues, are linearly independent, and there are n of them. Right, so any response can be written in terms of these mode shapes. Right, so here x is the response, and then these q's are the modal coordinates. Right, so essentially they're functions of time. So anything can be written in terms of linearly independent basis directions, right? So I'll take this and I'll substitute it into the equations of motion, right? So essentially we end up with m times sum from j equals 1 to n. Now we're taking the second derivative, so we have q double dot. Remember, the mode shapes are constant. Only the modal coordinates depend on time. And then we have our stiffness term. Again, sum from j equals 1 to n. And this is just qj times uj equals f of t. So at the moment I haven't really done anything, or at least I haven't simplified the problem, right? Because we still have n equations and they're still all coupled together. But we'll now make use of this orthogonality of the mode shapes. Right? So I will come along and take this whole equation and pre-multiply by ui transpose. So when I do that, this gets distributed into the equation of motion, and this simplifies to sum from j equals 1 to n. And now we have ui transpose times m times uj qj double dot. Well, this we've seen before. And this will simplify considerably. And we have the same thing for the stiffness term. Ui transpose times k times uj qj. And this equals ui transpose times the forcing vector. So again, this simplifies considerably because even though we have n terms here, all but one, right, assuming that lambda I and lambda j are not the same, so we have distinct eigenvalues, which we typically do. All of these, except when j is equal to I, are 0, right? If I was 1 and j was 2, well, because of the orthogonality, that would vanish. So this reduces down to ui transpose m times ui qi double dot ui transpose k ui qi equals ui transpose times f. So now we have just a single scalar equation, and here I is, I can be anything from 1 to n, where this amounts to a single degree of freedom forced undamped system. Right? So again, we end up with a set, and the set is obtained by changing I from 1 to 2 all the way up to n of n uncoupled one degree of freedom systems. And here, these Q's are referred to as the modal coordinates. So we can actually simplify this a little further. Right? So here it is again. This was our single degree of freedom modal equation. Right? And again, I would be taken over all the indices. Right? So for each value of I, we get a different equation. I want to recall the eigenvalue problem. Right? So let's remember what that looked like. It was k times uj equals lambda j m times uj. Right, so again, this was the eigenvalue problem that gave rise to the eigenvalues and the eigenvectors. So I'll come along and pre-multiply by ui transpose. Right, so this could be a different, or it could be the same eigenvector as uj. So when I do this, I end up with ui transpose times k uj is equal to lambda j ui transpose times m uj. Now, again, orthogonality, this is equal to 0 if I is not equal to j. But if I is equal to j, then these quantities are non-zero. However, we can then go and show that ui transpose times, in this case, k ui. So basically I'm substituting I in for j. This ratio is precisely equal to lambda I. This is known as Rayleigh's quotient. And can be generalized to be very useful in finding or approximating eigenvalues. But so here we have the ratio of u k u to u transpose m times u. Well, let's go back up and just divide through by this term in front of q double dot. So the equation of motion for the ith coordinate looks like the following. We again see this ratio qi equals ui transpose times f divided by, and again this u transpose times m times u, so this quantity here. So now we'll make use of Rayleigh's quotient, and that represents effectively the stiffness of this modal equation. So this simplifies to qi double dot plus omega I squared times q equals some forcing gi. Again, I is 1 to n, and here omega I is the square root of lambda, and the forcing term is just this right hand side here. Right, so it's ui transpose f divided by ui transpose times m times ui. Again, this looks fairly involved, but once we know the eigenvalue solution, right, so once we have these values of lambda and u, then all of this can be calculated. We can take the eigenvalue and use that as essentially the square of the natural frequency. We can use the eigenvector to determine the modal forcing. Right, so again, this is the modal forcing. And this is the modal frequency. And this is the modal equation. Well, we can solve this. And ultimately find the modal solution. So that would be q of t, which again, let's go back to our little flowchart. Once we have these q's here, we can reconstruct the solution to the original equation of motion. So let's talk a little bit about the modal coordinates themselves. Right? So these can be written in terms of the physical coordinates. And so the physical coordinates are represented by x of t. So that's that vector of coordinates. And again, thinking back to our decomposition, right, we wrote x as q1 times u1 plus q2 times u2 all the way out to qn times un. So you can probably guess what we're going to do here to isolate an individual q. We'll pre-multiply now by ui transpose times the mass matrix, right? Because we need that orthogonality of the eigenvectors with respect to the mass. I could use the stiffness as well in here, but then I'd probably have some different values of lambda floating around. But carrying this through, right, we see that ui transpose times m times x. Right, so again, once I know the mode shapes, or the eigenvectors, I can calculate this left-hand side. And this is going to be now the sum, j equals 1 to n, of ui transpose times m times uj. Right, so here j is the 1 or the 2 or all the way up to n, times qj. And once again, we see that this is 0 unless I is equal to j. So this reduces to ui transpose times m times ui times qi of t. As a result, we can find the modal coordinates in terms of the physical coordinates. Right, so qi is simply ui transpose m times x, and x is the vector of coordinates, divided by ui transpose m times ui. So this is particularly useful for initial conditions. So if I just evaluate this at time equals 0, right, we can find initial conditions on the different modes, given the initial conditions for the system. Right, so qi of 0 is ui m times the initial displacement divided by ui transpose m times ui. And we have the same for the initial velocity. Right? Just take the derivative of this with respect to time. Well, the only things that depend on time are q and x. Right? So q dot is ui dot m times x dot initially, so the initial velocity, divided by ui transpose m times ui. So again, we can take here initial conditions for the system, and turn that into initial conditions for the individual modes. Right, so we'll represent that initial displacement of, say, mode I is the right-hand side here. Right, so that'll be qi 0, and we can do the same to find the initial modal velocity. qi 0 dot. And of course, we would do this for each mode. I equals 1 to n. So again, this modal transformation can be used for the coordinates as well. And this is actually useful because now we can determine how the different modal coordinates are represented in terms of the actual physical coordinates. So I want to do an example, and this is an example that we've seen before. We have two blocks, right, identical, connected with two springs, again, identical stiffness, in a chain, and now I'd like to apply a force to the rightmost block. So I'm not going to go through and derive the equations of motion again. We've done this previously with the exception of the force, but if you're having trouble, maybe go back and recreate the equations of motion, use Lagrange's equations. But we end up with mx double dot plus kx equals f. M is the mass matrix, right? It's given here. X is the coordinate vector, and we'll take the first element as the displacement of block 1. We'll take the second element as the displacement of block 2. The stiffness matrix is given, and then the forcing term is 0 applied to the first equation and f of t on the second. And then previously, again, we've done this problem and we looked at the solution, and the eigenvalues and eigenvectors are given here, right? So lambda 1 is 0.382 times k over m. Again, k is this unknown or variable stiffness, and m is the mass. And we have the first eigenmode, or we have the first mode shape. This is an in-phase mode, according to our previous definition. And the second mode is an out-of-phase mode. So if we go back and we look at what we had done previously, let's go back and look at this. We have this quantity, right, u transpose times m times u, that appears frequently. It's here in the modal forcing. It's here in the initial conditions. So let's go ahead and calculate that. That's something that we're going to need as we go through and solve for the response. So we can calculate this, ui transpose times m times ui. Well, u1, and let's do this for I equals 1. And it's actually, that's 1.618 times, now the mass matrix given here, and then u is 1.618. Right, so notice this first term is a row vector, a 2 by 2 matrix, and then a column vector. So that reduces to, well, let's do the second part first. So 1.618, and then we have m and 1.618 when I multiply that matrix and vector together. So we have m plus 1.618 times m, well, that's squared, times m when I multiply these two together. And that ends up being 3.618 times m. Right, so this quantity here is 3.618 times m, and we'll keep that around because we'll need it later on. Likewise, we can do the same for u2, so for the second mode, and we find that this is 1.382 times m. Right, so I kind of did this ahead of time. All right, so now we have the modal equations, right? And this was from our previous work. Here, right, these are the modal equations. This is G, the modal forcing. And again, omega squared is the eigenvalue, right? So let's let the forcing be harmonic, right? So f of t is some amplitude times sine omega t, right? So just a harmonic forcing. And this frequency is the excitation frequency, which is distinct from the modal frequencies. These are specific values, right, that depend on the system. This is the forcing frequency that, in what we'll do, will allow to vary and determine how the response changes. So let's go and look at the individual modes, right, and how they respond. Right? So for mode 1, the modal equation ends up as Q1 double dot plus 0.382 K over M times Q1 equals, well, so when I work this out, let's go back and remember that the lambda 1 is the natural frequency, or the eigenvalue, and the mode shape was 1 and 1.618. So when I calculate this quantity, I get 1.618 times f of t divided by this quantity again, which we saw on the previous slide was 3.618 times m. So when I work this out and I combine all this, I get 0.447 times f naught divided by m times sine omega t. So this is the equation for mode 1. And now I can look at mode 2. And we have Q2 double dot. The modal frequency now is 2.618 K over M. Well, so the actual modal frequency is the square root of this. And then working out this forcing, we now get minus 0.618 times f of t, and then 1.382 times m. So this reduces to now minus 0.447 f naught divided by m sine omega t. It just so happens that these modal forcing terms in this problem have equal magnitude and opposite sign. In general, that's not true. Like I said, it just happens in this problem that it works out this way. So don't expect this to be true at all for all the problems that you may solve. So now, if I look at both of these, they are single degree of freedom systems, right? No damping with harmonic forcing. So we can solve the two of these together, right? So if I have a system that looks like Qi double dot plus omega I squared, Qi equals some forcing, G sine omega t, then the general solution here becomes Qi is some amplitude, which is G divided by omega I squared minus omega squared sine omega t. So remember, this is the modal frequency, omega I, and omega is the excitation frequency. So this quantity in parentheses represents the amplitude of the modal solution. We'll call it capital Q since we're using little q as the coordinate. So each mode will respond for the particular solution as a harmonic function with some amplitude. Now, we have not discussed the homogeneous solution here. We're just looking at the particular solution for these modal equations. So now let's go and see what those would look like. I'm going to choose some values. We'll let m, the mass, be 10 kilograms. We'll let the stiffness be 2,000 newtons per meter, and we'll assume the forcing amplitude is 40 newtons. These are just, I just made these up. And as a result, we find that the first natural frequency is 8.74 radians per second. And so Q1, again, using this expression, remember G is the forcing amplitude, and then we have an omega squared, which is the modal frequency minus the excitation frequency squared. Right, so this is the response, the particular solution, for the first modal coordinate. And we can actually simplify this a little bit. With these numerical values, we end up with 1.788. And then in the numerator, we have 76.4 minus omega squared. 76.4 is the square of the modal frequency times sine omega t. And so, just to remind you, Q1 sine omega t, where Q1 is this term in parentheses. So what I want to do is basically plot the modal amplitude as a function of the forcing frequency. So now notice that if the forcing frequency is equal to the natural frequency, this grows unbounded. And as you create the response, you end up with something that starts off at some value and then blows up as you approach the resonant forcing. Now for omega greater than this value, well, the denominator here is negative, right? So the response actually ends up with a negative amplitude and then just drops to 0 as omega increases further. Right? So as omega gets really large, the denominator here is negative and large. Right? So the response goes to 0. For the second mode, right, we can do the same thing. And this reduces to minus 1.788 divided by now 523, which is the square of the natural frequency, minus omega squared sine omega t, which again, modal amplitude sine omega t. So this mode 2 blows up when the excitation frequency, the forcing frequency, is equal to omega 2. So now we have something that looks like this. This starts off as negative, right, because of this negative here. And then it blows up when omega is equal to omega 2 and becomes positive for omega greater than omega 2. So this is essentially how each of these two modes responds to the forcing. But of course the overall solution is a combination of modes. So if we want to talk about how the system responds, I need to go back and reconstruct the original solution. Right? So here Q1, some amplitude, sine omega t. Q2 is the amplitude, sine omega t. And here I've redrawn those. This was the amplitude of mode 1. This is the amplitude of mode 2. So the overall response is just, again, reconstructed as Q1 times U1. U is the first mode shape. Q2 times the second mode shape. Right? So in terms of the coordinates that we've chosen, x, again, was the displacement of the block 1, and y is the displacement of block 2. And that's going to be Q1 times the first mode, which was 1.618. Right, so again, this was the mode shape that we found from our modal analysis, or from our eigenvalue problem. Q2 is the amplitude of the second mode, and the second mode shape is minus 0.618, and then sine omega t. So with this harmonic forcing, both x and y, the displacement of the two blocks, behaves harmonically, but the amplitude of those two is different. So again, here I have drawn in light blue the amplitude of the first mode times the mode shape, right? So this first panel is the amplitude of x, so the displacement of the first block, right? So blue here is 1 times Q1, and the purple is 1 times Q2. So now the overall response is simply the sum of these two things. So I'll just add them up. Right? And what we find is that it ends up looking something like this. Now notice that x is singular whenever we're forcing at either of any of the resonant frequencies. And then if I look at y, so the second block, again I'll just add these two together. But something interesting actually happens here. We have a resonance whenever we force at one of the resonant frequencies. So here this was 8.47 and this one was 22.88. But we also have in Y what we call an AntiResonance. That's actually fairly interesting. The response amplitude of the second mass is 0. Right, so here, let me go back and look at the physical picture here. So now, for that one special frequency, I am forcing the system. Block 1 was moving around. Block 2 remains completely fixed. It does not move, right, at this value of the excitation, which is roughly 18.5. So at this anti-resonance, again, block 1 is moving around, right? That would be, say, this value here. But block 2 is completely stationary. This is kind of interesting. And actually has practical application for vibration isolation. Right? But these are two of the interesting features that can occur in the response of the system as we vary the forcing frequency. Here we have each modal solution blowing up, and this anti-resonance, effectively the two modes interfere at the second block and produce zero response. So this is a quick introduction to modal analysis. With modal analysis, again, we are able to decompose the system into the response of the individual modes, even with forcing, and then we're able to reconstruct the response of the original system. In doing so, we would turn a set of n-coupled equations into a set of n-uncoupled equations, which end up being much easier to solve. Okay, so again, just a brief introduction to modal analysis. Thank you very much, and I will talk to you again. Bye.